Okay, so looking at 1 over x plus 3. If x is near negative 3, then x plus 3 is near 0, right? So x values close to negative 3 are the values that give us small values of the denominator that go into the numerator lots of times. So that 1 over x plus 3 is the reciprocal of a small number. If x is near negative 3, 1 over x plus 3 is the reciprocal of a small number, which is large. And also, 1 over x plus 3 is a horizontal shift, negative 3 units relative to the graph of 1 over x. So that if we take this graph and shift it over 3 units, well, we get a graph that looks a lot like this. Okay? When x is near negative 3, you get a large value of y, as we say. And also when x is a large positive or large negative number, 1 over x plus 3 is going to be small. So this is kind of how we can just understand the graph of 1 over x plus 3. And what I've indicated with this little purple segment here is this little purple segment consists of x values that are close to negative 3. And those x values on this side of negative 3, well, that'll make x plus 3 positive but small, giving us a positive but large reciprocal. On the other side of 3, the values of x plus 3 are negative, giving us large negative numbers when we're close to negative 3 on that side. Okay, now we want to use these ideas with a graph of a rational function. This is a simple rational function. Okay, f of x equals x plus 1 over x minus 2. Now we can make a couple of observations about this. Let's look first at the denominator. You can understand that if the denominator is small and the numerator isn't, you're going to get a big positive or big negative value. So you're going to have the graph going way up or way down. Well, if x is close to 2, our denominator will be small. Okay? And if x is close to 2, the numerator, x plus 1, well, if x is near 2, x plus 1 is near 3, isn't it? So for x values near 2, the numerator is close to 3, so x plus 1 over x minus 2 is near what? 3 divided by a small number. So it's large. Now, if x is a little bigger than negative 2, x minus 2 is positive. So you're going to have 3 over a small positive number, which is going to be a big positive number. If x is a little bit less than 2, then x minus 2 is going to be a small negative number. So you're going to have a number near 3 divided by a small negative number, giving you a large negative value. Question now, what are the values of this function if x is large? Okay. Well, if x is a really big number, then x plus 1 is much bigger than x, and x minus 2 isn't much smaller than x in proportion. Okay, if x is 1,000,000, you got 1,000,001 divided by 999,998. That's pretty close to 1,000,000 divided by 1,000,000. And that's close to 1. So when x is really big, there isn't much difference between the numerator and the denominator, and the quotient is going to be close to 1. So if x is large, x plus 1 and x plus 2 are about the same, so x plus 1 over x minus 2 is about 1. Okay, what else can we find? Well, we always want to find the zeros of a function. So when is f of x 0? And I said near 0, but really we can find when f of x is equal to 0. Well, it's equal to 0. The only way it's going to be equal to 0 is if this numerator is 0. Because the only way you can get 0 by dividing a numerator by a denominator is if the numerator is 0 and the denominator isn't. Well, if the numerator is f of x is 0 if and only if the numerator is 0, I should say if and only if the numerator is 0 and denominator isn't. Okay? Well, clearly if f of x is 0, then x is -1, and the denominator would be -1 minus 2, which is -3. So the denominator is not equal to the numerator. So the denominator is not going to be 0 when the numerator is. Okay, so numerator 0, that occurs when x equals -1 because x plus 1 equals 0 is easily solved. You get x equals -1. So f of x is near 0 if x is -1, and f of x equals 0 if x is -1. Now, what does all this tell us about the graph of this function? Well, it tells us if this is the x-axis and this is the y-axis, that over here when x is -3, that's where these values blow up. So you're going to have a vertical axis here, a vertical asymptote. Vertical asymptotes, both sides, negative on this side, positive on this side by what we've already said. When x gets really large, the value of f of x approaches 1. So we've got this infinite horizontal line, x equals 1. When x gets really big, the graph has to get close to this line, and when f gets really big in the other direction, the graph's going to get close to this line. Okay, well, there's a little more that we can determine. We also determine, of course, that the function is 0 when x is -1. And we can also plug in x equals 0 to see that it's equal to 1 over -2, which is -1/2. When x is equal to 0, there's your y-intercept. So we have these 2 points that are on the graph. We have you know what, I drew if something wasn't working out, because this graph just isn't going to go together. Okay, we determined, I looked at my numbers, we determined that the denominator is 0 when x is near 2, not 3. I caught that out on the corner of my eye and shifted it the wrong direction. So here's x equals 2, and this is where our asymptotes are going to go. Okay, so we can already see what's going to happen to the graph of this function. Okay, it's got to go through these 2 points, it's got to approach this line, and it's got to have a negative asymptote here, so it's going to have to look something like this. Over here. Over here, it's got to come down from a positive asymptote and then be asymptotic, a positive vertical asymptote, and be asymptotic with the line x equals 1, which is going to tell us that the graph is probably going to look like this. Okay? Now we're going to construct it in a little more detail because we want to look at where the graph is positive and where it's negative, and we want to get used to how to analyze that before we do a final version of the graph, but it's going to look a whole lot like this.